Hey guys, here we are in section 3.4, and what we're looking at is linear programming. Today we have a few vocabulary words, and these all will refer to the idea of graphing inequalities on a pair of axes. So I'm just going to draw this really quickly, kind of what we've been working on before. You guys remember? So we would draw one particular inequality, graph it rather, and then we graph another one, and it might do something like this, and yet another one may be doing something like this, right? And what we get when we graph these inequalities is we get a region, right? A specific place where all of the inequalities can be satisfied. That is referred to as the feasible region. All right, that's the feasible region where we can find answers to the question that we're looking for. See, what linear programming does, it takes word problems, we break it down into inequalities. Those inequalities are considered the constraints. So those inequalities are going to be used to model the information that's given. And so the information might be, well, you'll see in a few minutes what that's going to look like. But so those inequalities that we use to create the feasible region will be where we'll get them through looking at our constraints. Bounded is when we have a region that is not open, right? There is no opening here. It is completely bounded by these lines here, all right? And that's what's happening here. The vertices we know to be the corner points, right? So our vertices, maybe I should be using color here. Our vertices would be these guys right here. Unbounded, we saw examples of that in the last video where we had areas or regions that would go on forever, infinitely. And linear programming, that's the type of problems we're going to do, and you'll see a really good example of it in the last example. Let's get started with our examples so some of these terminologies make more sense. So here we are with example 1. We're going to take a look at a bounded region. And they want us to graph the following system of inequalities, and we're pretty used to this. And we're going to name the coordinates of the vertices of the feasible region. We're going to find the maximum and minimum values of the function. And what we're going to do is we're going to find that given this particular equation. So what this equation is, it's going to be dependent on x and y. So I need to plug in both x and y in order to find what the maximum value is. We use the maximum value, or we use only points found on as vertices. Let me show you what I mean. So if we take the first equation, let's call this one green, and we're going to graph x is greater than or equal to 1, we know that the corresponding, or what I say is the related equation, would be x is equal to 1. So what I'll do is I'll first graph that. X is equal to 1. That's a vertical line that goes to the x-axis at 1, right? That's the graph of x is equal to 1. And since it's equal to or greater than, I know that it's a solid line, and I'm going to shade everything to the right. Just like that. After doing this, I'm going to go and I'm going to look to find other information, or use the other, what we'll call them as constraints, which are our inequalities, right? We're going to use the other constraints in order to graph the rest of this. So here we find out, let's call this the blue equation. We find out that, or blue inequality rather, we find out that y must be greater than or equal to 0. Well, where is y equal to 0? We remember y equals to 0 is a horizontal line at 0 that intersects the y-axis at 0, which also happens to be the x-axis. And so what I'm going to do now is shade up from there. And you remember, anytime we're dealing with these types of inequalities, we're really concerned about the overlapping region. So you know, right now we're concerned about this region here that's kind of blue and green. Next, we'll do this last equation. This guy, our red one, let's make it red. Our red equation, we'll solve for y first. After solving for y, it makes this red equation a little bit easier for me to graph. My y-intercept here is going to be 6, and my slope is going to be -2. 1, 2, 3, 4, 5, 6. I start here. My slope is -2, so it goes down 2 and over 1. And I did call this a red equation, so let me draw the line in red And notice that we're going to shade, let's see where we're shading. We are shading below, right? Below the red line. And when I do that, I get a little corner piece here that is my feasible region. There, so I took the liberty of moving in closer so you guys can see that here, this triangle right here, I'm going to highlight it in black. It's not usually a color of highlighting, but you get where I'm going. This region here is the feasible region. This is a region of concern. So this little section here is where all of these inequalities are satisfied. And because of that, it's really important for us. Linear programming teaches us that these corner points are the only place where there's infinitely many points here. You guys know that, right? Infinitely many points all up in this section. I'm going to try to shade this in a color that that can stand out. None of these colors are standing out. It's too many colors. Let me try again. Let's see. So this little, I'm going to just make it a dark green here. This little green triangle has infinitely many points here. We want to find the point that maximizes this equation. And what linear programming tells us is that the only points that will maximize that equation will be these corner points or these vertices. So that's great because we don't have to try infinitely many problems in order to solve this. So let me isolate the points that we're dealing with here. The first point is 0. Oh no, it's 1, 0. That's this one down here. The next point is 3, 0. And the final point that we're concerned about over here is going to be 1, 4. 1, 2, 3, 4. 1, 4. All right. So now I've listed all of my points, these corner points, these vertices, and I'm going to plug them in to find out what the corresponding f of xy value is. So this is a function that requires me to put in both x and y, and when I do that for this particular one, for the first one, I get that my final answer is 3, plugging in 1 here and a 0 here. The next one, when I plug in a 1 and then a 4, I get the answer 7. And finally, when I put in 3 and 0, I get the answer 9. So I see that the maximum value here is going to be found at 0.30 and I will get 9, right? So that's what they're asking us to do here. We'll have a couple of examples that have a more real life or realistic application, but that was just an example so you can kind of get used to the method. Let's go through really quick what we did. We graphed everything. We figured out what those vertices were. We used those vertices in order to put into the function that we needed to maximize. We plugged in those values and we figured out what the maximum value is. And so we figured out the point that would yield the greatest value in this equation. All right? Let's take a look at this next one. So again, we're going to do the same thing, and I've taken the liberty to solving for y in each of these inequalities, and I've already given them color. So let's get started with graphing them. So there's that first equation graphed or inequality graphed, and let's do a couple more. Okay, so that looks crazy, but this is our graph. This is what we have. I had to go actually off the y-axis and kind of count up because my y-intercept was 10 for this orange inequality and then shade down. But can you notice something about our region or our answer region? Our answer region here is actually right in here where all three graphs overlap. And what we're noticing, I'm going to just do that and do this here and do this here. And what we notice is that these points are the only vertices because this is an unbounded region. It continues on and on forever and ever in this direction. So notice this point was pretty easy for me to find. I could see that that was just 0, 3, but the question is, what's this point over here? So I got to figure out what that's going to be also. So how can I figure that out? I've got to figure out the intersection of the orange line and the purpley pink line. I'm going to solve using systems of linear equations. I'm going to solve using elimination method. So I get 7y is equal to 28. And remember, I'm looking at the intersection of this orange line and this guy. And so that's why I'm using those two equations. Therefore, y is equal to 4. That's what we have here. All right, so now with that, we're going to take our 4 and we're going to plug it right back into the equation to figure out a corresponding x value. So 2x, I'm going to take this orange equation, plus 4 equals 10. Subtract 4 on both sides. I end up with 2x is equal to 6, and therefore x is equal to 3. So this point is going to be, looks like my graphing was pretty much off, but it's going to be 3, 4. So these are the 2 points that I can check, but realize that this is an unbounded region, and what we're looking for here is we're looking for not only the maximum, but we're also looking for the minimum value of the function. So the 2 corner points are going to be really helpful for us. Let me set up a little chart for us. So when I plug in 0, 3 for this point, for this equation, I'm going to end up with 12. And when I plug in 3, 4 for this equation, I'm going to end up with 20, let's think, what is that? 15 plus 16 is going to be not 20 anything but 31. And so 31 is the maximum value that we have. The question would come up, well, since it's unbounded and we're looking for a minimum value that would satisfy, does it make sense to think about any of these other values down here? And if we were to choose another value here, let's say this is 3 negative 1, right? If we chose 3 negative 1, do we get a smaller value than 12, which is a decent question. If I plug in 3 negative 1, I do get a smaller value. I get 15 plus a negative 4, which gives me an 11. So what this basically tells us is that we don't actually have a minimum value when we have it unbounded in a way like this. I think that's a little bit tricky, but we'll talk about that a little bit later in class. But that's what we have. So we don't have a minimum, but we do have a maximum. We can feel confident about our maximum. So take a moment to read over this problem and we will talk about it, all right? After taking that moment to read, you're going to realize that there's a lot of variables going on, or at least it feels like a lot of things are going on. But what we are asked here is to figure out what are the how many surgeries and how many regular visits or regular office visits do we need to have in order to maximize the financial situation for this particular office. So those are the 2 variables. But the best way to figure out your variable is to look at what the question is asking and then kind of think, okay, well, those must be the 2 things. So let's use X for the number of surgeries and Y for the number of office visits in this day. And then what we'll do is we'll use that information to kind of get the constraints for the situation here. So I know you read it and you probably read it again. Let's look at some of these things line by line. So it says that the office receptionist reserves 20 minutes for office visits and 40 minutes for surgeries, but there's only 7 hours available for appointments all day. Let's change the hours to minutes. So that's 420 minutes. And now we can say that if we have 20 minutes for each of the office visits and then 40 minutes for each of the surgeries, X, then we know that that has to be less than or equal to 420 minutes, which is all the time that I have in the day. Take a moment to think about that, and you will see that it makes a certain logical sense. The next bit of information we need to know is that the veterinarian cannot do more than 6 surgeries per day. That means that the X value has to be less than or equal to 6. Also, we can say that the Y value has to be greater than or equal to 0. And maybe I could say the same, that the X value has to be between 0 and 6, because you can't think of negative values like a negative number of surgeries or a negative number of office visits. So the next thing we're going to do is graph it and try to find our feasible region. So I color coded them, rearranged this one so I could graph it pretty easily, and here's the graph of that constraint or that inequality. Let's do the others. Here's our blue constraint or our blue inequality that refers to surgeries. And here's our purple constraint as well. And so the next thing we need to do is check out the boundary markers on each of on this particular feasible region. And so these points were easy to find. I didn't have to do any systems of equations. And this wasn't too hard to figure out either, given that each office visit is charged $55 and each surgery is $125. Okay, so when I calculate this, and I had a mistake here earlier, these should have been sixes because I didn't look properly at my graph. When I calculate this, it's noticeable that it's best for this office to go for 6 surgeries and 9 regular office visits to get the maximum profit of $1,245. All right, that's it for me. Let me know if you have any questions. Take care.